All right, so today, see if how much boardroom I have here. The topic is partial fractions. And the bad news is it's pretty complicated. It's going to take 2 lectures to present it. So you can maybe start a little of the homework after this one, but maybe wait till next time to do the rest of it. The good news is there's no calculus in it. Why are we doing this in calculus? It's all algebra. What it does is it's an algebra method to make integrals that you couldn't do before into a form that's easier to integrate. So it will actually improve our integration techniques using algebra. So we'll say this, partial fractions I've got some more to let in here, hold on. Partial fractions is a pure algebra method. It's the algebra method actually of undoing a common denominator. How about that? Your algebra teacher always told you to put this over a common denominator. In calculus, we're going to make it go the other direction. It's just like being in the army, right? Sarge says, move that pile of rocks over there. And you say, I'm all done, Sarge. Right? And okay, move them back for the next guy to do it. That's what we're going to do. It's the algebra technique of undoing a common denominator because it'll make our integrand easier to evaluate, easier to integrate. One more here. And it works like this. For example, this will be our first example today. Suppose I wanted to integrate this. 2 over x squared minus 3x plus 2. All right, that's hard to integrate. All right, we don't have good techniques for that yet. But what if I told you it can be rewritten like this? Some number, we don't know what it is yet, over x minus 2, plus some other number over x minus 1. Partial fractions actually says that for some numbers, a1 and a2, we'll have to figure out what they are. This is true. Huh? Sorry, the waiting room is keeping people out of class, so I have to keep letting people in. All right. So then I can integrate each of these, right? I can do this. If I had to integrate this, I can do it with the u substitution. A1 is a number. So I just let u equal x minus 2, and this becomes integral 1 over u. That's a logarithm. That's easy. Same thing with this one. Let u equal 1 over x equal x minus 1. This is 1 over u, and I can integrate that as a logarithm. So that's the idea of partial fractions. Take something that was hard to integrate, use algebra to rewrite it as something that's easier to integrate. Here is the theorem for partial fractions. And it's very complicated. If you don't understand it all, that's fine. The object is to write it all clearly. So when we do the examples, you can go back and say, oh yeah, that's what it meant, right? So, but when you come, when you start to do the examples, then this all makes sense. So here's the partial fractions. A quotient of polynomials. Maybe you remember what polynomials are. We deal with them all the time here. They're very important in algebra and nice in calculus because they're easy to work with. Nice in lots of things because they're easy to work with, actually. A quotient of polynomials, what is that? Also called a rational function in algebra, is a number times the whole power of x plus a number times the whole power of x plus dot, 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 plus a number times x plus a number. We call that a polynomial, right? Where the ands are just indexed constants, right? So it's a constant times the power of x plus a constant times the power of x plus a constant times x to the first plus a constant. That's a polynomial. A quotient of polynomials or rational expression is one polynomial divided by another. So I've got bkx to the k plus so on and so forth plus b1x plus b0. There's a quotient of polynomials, and these things we can rewrite just like we did there and find a way to integrate these complicated expressions that come up quite a lot in practice, actually, even if you take a numerical methods class where you learn computer methods to solve math problems. These are used a lot because polynomials are easy to work with. And so you want to be able to do these kinds of things. All right, so a quotient of polynomials of this form with n less than k, the degree of the numerator, the highest power in the numerator, has to be less than the highest power in the denominator. This one can be expressed as a sum using the factored denominator. For each, what we call a linear factor of the denominator, when you factor the denominator, this is a factored form here. Each linear factor, ax plus b, we call that a linear polynomial or a linear expression, ax plus b, a number times x plus a number, say taken to the kth power in the denominator. You don't even worry what's in the numerator. As long as it's lower power, this will tell you the form of the sum. So each factor of that form in the denominator, I'll abbreviate it here. You write this sum, a number over ax plus b plus another number over ax plus b squared plus dot 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 plus another number over ax plus b to the k. All right, and so if you have this factor occur k times, you have to write a sum that includes all of these. It's starting to look complicated. I know it doesn't make sense yet, but it will, right? And then I need a better eraser than this. Like, maybe it's the best I've got. Hate to mess up my pristine board here. This. Now also, for each what we call irreducible quadratic factor. A quadratic is a second degree polynomial. It's just an ax squared plus bx plus c. An irreducible quadratic ax squared plus bx plus c is a quadratic ax squared plus bx plus c with negative discriminant, b squared minus 4ac less than 0. Remember what happens when this discriminant is negative? It means you can't factor this using real numbers. So that's as far as you can factor it. Every polynomial, including this denominator, factors uniquely as a product of these linear factors, ax plus b, and these irreducible quadratics, ax squared plus bx plus c. Now this might occur k times also, right? Some k number of times. And when it occurs, when an irreducible quadratic that doesn't factor any further over real numbers is left to the kth power, you write this kind of a sum. You write a b1x plus c1 over the irreducible quadratic plus b2x plus c2 over the irreducible quadratic squared. What a mess, huh? Plus bkx plus ck all over the irreducible quadratic of the k. This is the most general thing you have to do because every polynomial factors into linear and irreducible quadratic factors. You won't get any cube terms left if you factor it all the way, it turns out. Theorem from algebra. So we're going to learn some real important algebra theorems today too, to remind you of them at least if you knew them. And what you do is you take, for every linear factor of the kth power, you write this, then you sum it with every irreducible quadratic to the kth power like this, sum all to get the partial fractions representation or equivalent expression that is always integrable. You always get something you can integrate. So that's the technique for today, is to take any quotient of polynomials where the degree of the top is lower and rewrite it in a frame in a way you can integrate it by just using an algebra technique to get there. Now, on top of this, in fact, we can do when the degree of the top is bigger or greater than the bottom. We're going to have to do that next time. I told you this is a long topic. But when the degree is at least as big as the bottom, then we have to do polynomial division. I'll remind you how to do that. You hopefully saw it in algebra. And then you can get a numerator's lower degree and then do this. So it actually works for any quotient of polynomials. But for today, we'll just do it when the degree of the top is lower because that's to what partial fractions alone applies. All right. So we'll emphasize that this can be reasonably integrated by our previous techniques. Now, if that's real confusing, yes, I know it is. We're going to do an example, and that'll really clear it up a lot. I got at least 2 examples I can finish today, and I hope this will really start to make sense at that point. So here's the first example, the one we put up there. Suppose I wanted to integrate 2 over x squared minus 3x plus 2. Alas, I don't know how to do that yet, right? But partial fractions to the rescue, right? Partial fraction says, what did I glean out of that theorem I just wrote down? 2 over x squared minus 3x plus 2 is a quotient of polynomials, right? This is actually a polynomial of degree 0. You can think of it as 2 times x to the 0. So that's a polynomial of degree 0 on top, and a polynomial of degree 2 because the second power is the highest on the bottom. Since the bottom power is greater, I know I can rewrite this as a sum, but first I have to factor the denominator, right? So I factor the denominator according to the theorem. This factor is, if you use your techniques from algebra, is x minus 2, x minus 1, right? X squared minus x minus 2x is minus 3x plus 2. Partial fraction says that once I factor the denominator and it's higher degree than the numerator, I get, for each linear factor, x minus 2 to the 1, I get a over x minus 2, a1. And then for this linear factor here, I get a2 over x minus 1. And it doesn't matter what the numerator is, this is still going to be the form. The numerator is going to help determine what these constants are, though. So the idea is when I see this integral, I rewrite the integrand like this, and these I can each integrate by making a u substitution. I just have to find out what a1 and a2 are. And I'll give you a big hint on on doing these. These can be very grungy and long. There are online calculators that will do this. You just have to learn how to use it. On your calculator that I suggested you could buy if you wanted, you can use the expand command. Go back in there and I like to teach this in class, but it's hard to put in all the overhead online, so I don't think I'll even try today. But I'll just say, learn how to use your expand command on your calculator. On the TI-89 or the Inspire with the computer algebra system, CAS, you can use this command to do partial fractions for you. All right, so it's on the calculator. Check your answers. All right, expand on the calculator. We'll do this, or we can always do this by hand. It's not that hard. So I'll make that hint, but then we'll say by hand we can do this easily. All I have to do is multiply both sides by this denominator of the original quotient. Actually, I'd rather multiply by the factored form. Is easier. Suppose I take this equation this expression right here, and say these two are equal. What's a1 and a2? Well, if I multiply both sides by x minus 2, x minus 1, then the left side becomes 2, right? Of this equation. And I multiply the right side by x minus 2, x minus 1. And all I've done is multiply both sides by x minus 2, x minus 1. There it is. Now I group like terms and get zero on the left. Zero on one side is key to figuring this out. So I've got, well, actually, let's multiply it out in one step and then put this over in the other step. I didn't write this right. This A1 over X minus 2. And A2 over X minus 1, sorry. Sometimes I get talking, I'm not thinking about what I'm doing. All right. So there we go.
Dr. Stapleton,
Yeah.
you're starting to reach off to the side where we can't see you.
Oh, I'm sorry. Thank you. Appreciate that. There we go. Yeah, that's pretty far over, isn't it? So I multiply both sides of this through by X minus 2, X minus 1. And I get this. And now I'm gonna notice that the X minus 2's cancel and the X minus 1's cancel here. So what I've got is 2 equals X minus 1 times A1 plus X minus 2 times A2. Right? Now I'm going to multiply out and group like terms. So this is equivalent to this, is equivalent to, let's see, if I multiply here, X times A1 minus A1, that's multiplying that one out, plus X times A2 minus 2A2. And then I'm going to subtract this 2 over here to get 0 on the right. So multiply out and get 0 on the left, on one side. And now what you do is you group like terms. I think you can see the bottom of the board, can't you? Yeah. Okay, so now you've got equivalently 0 equals the X term times something. Let's say something times X plus something, grouping like terms. All the X terms are A1 plus A2. All right. And then the constant terms, minus A1 minus 2A2 minus 2. There it is. All this equals 0. And now you realize an interesting fact. This has to hold for all values of X, except 1 and 2 where it's not defined. In order for this to hold for all values of X, virtually, it has to be that this number multiplying X is 0 and this number over here is 0, right? If I put a number times X plus a number equals 0, how many solutions does it have? It has exactly 1, right? If I put 3X plus 2 equals 0, then X is minus 2/3. That's the only solution. So Ax plus B equals 0 always has only one solution. Unless maybe I put this equals 0 and have a number equals 0, then there's no solution. The only way I can do it is if both of these coefficients are 0, right? The coefficient of X and the constant term are both 0. So let's say this equation, in order for it to hold for all values of X, is equivalent to requiring that A1 plus A2 equals 0, the coefficient of X is 0, and also this one, minus A1 minus 2A2 equals 2. Let's put it that way, so that this one is 0. Right? So this has to be 0, and this has to be 0. Well, look what we've got. We've said that this requirement that we write this in partial fractions form is equivalent to the system of 2 linear equations and 2 unknowns. Probably very few of you have had a linear algebra class so far, but in linear algebra you can show that in fact this will have a unique solution when it comes from partial fractions. So if I call those equations 1 and 2, when I go to solve these partial fractions, unless I made a mistake, it will always have exactly one solution. How can I solve that? There's 2 popular methods. One of them is substitution. I could write A1 equals minus A2 and substitute in for A1. Here, get an equation just A2. A substitution is fine. Do that if you want. I'm not going to do that here for an interesting reason, is that when you have more complicated denominators here, you can get 3 equations and 3 unknowns, or 4 with 4 unknowns, and so on. And those, substitution becomes too cumbersome. Substituting for A1 and then getting A2 in terms of A1, in terms of A1 and substituting in and getting A3 in terms of those, it becomes very long. It's an arduous process. What's easier here that most people do instead is elimination, because elimination for 3 equations is not so much harder than for 2 or for 4 equations. So I'm going to use what's called elimination. If you've heard of Gaussian elimination before, that's an orderly process that makes this elimination always work even on a computer, as long as you can do enough precision. So elimination works also, and it tends to be faster for larger systems of equations. Elimination, what you can do is add a multiple, one equation to another to eliminate a variable, right? So suppose I take equation 1 plus equation 2 and add them together, right? If these two left, if this is equal to this and this is equal to this, then the sum of these has to be equal to the sum of these. That's what we're saying. So I add these two down, A1 and minus A1 is 0. A1 goes away. That's why I added the two. I added them to make the A1 go away. Then I take this one plus this one gives me minus A2. And this one plus this one is 2. And I've discovered now that A2 is actually negative 2. So I've got one of the two numbers. Now I can substitute it into either equation, take the easier one, to put it into 1. Result that I have here, and I have A1 plus negative 2 equals 0. Apparently, from that, A1 equals 2. So now I've got the coefficients. What I've found out is by algebra alone, there's no calculus at all in this. We found out that the original quotient, 2 over x squared minus 3x plus 2, will be A1, right, looking over here, 2 over x minus 2, plus A2, which was minus 2, over x minus 1. All we did was algebra. And now, go back to our original integral. Let's say hence, or now. All right. Now this one is equal to the integral of 2 over x minus 2 minus 2 over x minus 1. These are easier to integrate. So actually undoing the common denominator helps you with your integration. And that's the whole partial fractions thing. Take a nasty integrand, turn it into something easier to do by algebra. So how do we integrate these? We write the integral of difference as the difference of the integral to pull the constants out. This is twice the integral 1 over x minus 2 minus twice the integral 1 over x minus 1. Right? We do the simple rules first, and then we say, how do we do this one? We can make a substitution. Let u equal x minus 2, this becomes integral 1 over u. Easy, right? Du is then the derivative of this dx is just dx. Similarly here, we can let v equal x minus 1, and dv is the derivative of this 1 times dx. Let's just put dx. What I have then is twice the integral 1 over u du minus twice the integral 1 over v dv, and those are just logarithms, right? Integral 1 over u is natural log of u, and then if u can be negative, it's put absolute value, so it's 1 over, it's ln absolute value of u, minus twice natural log absolute value of v, plus now the constant when we drop the integral sign. There it is, and I can put back my v, u and v here to find out that this nasty integral actually is not so bad. It's twice the natural log of x minus 2, absolute value, minus twice the natural log of x minus 1, absolute value plus constant. There it is. I think SimiLab will Achieve will accept this answer. I'm not quite sure, but I do want to show you something in addition. Achieve is liable to not list it like that when you go back to look at their answers, or if you put it on one of these integral calculators online, it may not give it this form and say, oh no, I messed it up. Where'd I mess up? What happens after this is a lot of times people will use the properties of logarithms to simplify this. Let's use these properties of logarithms. By the way, stop me as we go as you have questions. I'll probably make this easier to understand if I get a few questions here and there. And I won't go as fast either, right? All right, so recall, however, from algebra, again, more algebra, right, that the if you take p times natural log of u, it's equal to natural log of u to the p, right? The power comes up. And also we have this property. natural log of P minus natural log of Q is natural log of P over Q. It works for any logarithm, but in particular, we're just simple natural logarithm here. So we can do that here. We can rewrite this as natural log x minus 2 squared minus natural log x minus 1 squared plus a constant, right? Because the p ln x minus 2 is ln of x minus 2 to the p with p equal to 2. But we're not finished, right? Because that was the first property. We put the multiplier up in the exponent. And now absolute value of x minus 2 squared is the same as x minus 2 squared. I can drop my absolute value, right? And I can drop it here too. Because it happens to be an even power, I can get rid of the absolute value. Do that when you have even powers here. Now we have the second property coming in. Ln p minus ln q is ln of their quotient. So you can write this as ln x minus 2 over x minus 1 squared plus c. And this is much shorter, well, a little shorter at least, when you write the answer. And this is what you're liable to see in the back of your textbook when you look at, like, if you do some of the problems in the text, check the answers in the back. They have the odd answers back there, I think. And then also online, you may get this answer instead of that one. But either answer is actually true, and I'll give you credit on the test for getting to there. But I like to see this form. It's simpler, right? Any questions on all that? Here's how you integrate a quotient of polynomials with the degree of the top lower. Factor the denominator. We did that. X minus 2, x minus 1. Based on those factors, apply the partial fraction theorem from algebra to rewrite this as an easier sum where you undo the common denominator. Then each term can be integrated by the techniques you have previously, and sometimes these logarithms are useful for combining the results. How about that? Now it starts to make sense, I hope. Right? That's the idea. Let's do one more here. So this is really powerful for quotients of polynomials, right? It does all of them. There is actually a drawback. There's a famous theorem called Abel's impossibility theorem, and that kind of puts a hitch in this catalog. Just when you thought you could integrate any quotient of polynomials, right? It turns out here's a fourth degree polynomial, right? Ax to the fourth plus bx cubed plus cx squared plus bx plus e. And here's a third degree polynomial, ax cubed plus bx squared plus cx plus d. This technique depends critically on your ability to factor polynomials, right? And so you can factor them when they're easy. But what happens is, even though if you have a quadratic polynomial like this, you can always factor it using the quadratic formula, right? You just write it as a times x minus the first solution of the quadratic formula times x minus the second solution of the quadratic formula. And this is the way this factors. You use the quadratic formula to find x1, x2. Similarly, there's a cubic formula for these that can always factor. There's a quartic formula for these. Nobody memorizes it. It's too complicated, but you can conceivably factor it. Abel's impossibility theorem says, remarkably, I like to point this out just so you have a feel for what's wrong with the method. Ax to the fifth plus bx to the fourth plus cx cubed plus dx plus e plus f, dx squared plus ex plus f. Polynomials of degree 5 or greater, there is no finite rule like the quadratic formula for finding the zeros of these, and hence no finite formula for factoring them. Which means if you get 5th degree or higher, you may not be able to figure out how to factor it. It does factor, you can prove it factors, but alas, you may not be able to find them. So this technique falls down when the denominator is 5th degree or higher because you may not be able to factor it. Hope is not lost because numerical methods can crunch numbers and get as close as you want to the solutions. If they're easy numbers, maybe you can guess them, right? So hope is not lost, but again, that factoring problem, you may not be able to actually find the factors exactly and do this exactly on some really difficult problems. Don't worry, we won't do those in this class. I just thought for the mathematicians here, it's worth realizing the technique always works provided you factor, and factoring is an impossibility problem for degree 5 and higher. It's a very fascinating story if you Google that online. I like to pique your interest just a little bit to look this stuff up. All right, let's do example 2 now. Suppose I wanted to integrate this x plus 1 over x squared times x minus 1. How about integrating that one? Well, once again, I'm stuck. All my other techniques don't work. I don't see it's not a sum or there's no constant to pull out. There's no integration by parts that looks obvious, or a u substitution. I don't see a function of a function to have a suggestion on that. But I just don't know what to do, maybe, right? What trig substitution? There's no square root x squared minus a squared or something like that in there. The hyperbolic functions don't even seem to apply. So what do we do with this? Oh, wait a minute. If I think about this, what this is it's x plus 1 on the top, and if I multiply the bottom down, it's x out, it's x cubed minus x squared. It's a polynomial of degree 1 over a polynomial of higher degree. I can use partial fractions to write this out, right? This is a quotient of polynomial. So partial fractions will work, and it's even better than that, because in this problem, the bottom's already factored, right? This is actually the factored form. So I'm on my way. By partial fractions, I rewrite the integrand, and then I integrate each term, and it will work, right? Since whenever I factor this always works. By partial fractions, I factor them through degree 4 at least. But by partial fractions, I know this, that x plus 1 over x squared times x minus 1 can be re-expressed as this. It's a1 over x plus a2 over x squared plus a3 over x minus 1. How did I pull that out of there? Right. The idea is this one is factored, and it's factored as x minus 0 squared times x minus 1. Think of it that way, right? It's ax plus b to the k, ax plus b. For each ax plus b to the k to the 2, you need 2 terms according to what we wrote down. Now that theorem is starting to come together, hopefully, right? Ax plus b squared, I need a number over ax plus b plus a number over ax plus b squared. And ax plus b is just x in this case, right? And then this one is the first power. I only need 1 term for it, a number over ax plus b, where ax plus b is x minus 1, 1 times x minus 1. All right, so this is the factored form. 2 terms for the factor that occurs twice, 1 term for the factor that occurs once, both linear factors. We'll do the irreducible quadratic factors next time. I won't have time for them this time. Looks like we're going to be a little short for that. But every denominator always factors into these linear factors and those irreducible quadratics. That's a theorem from algebra. And so this technique will always work if you can factor it. And here's how this one factors, right? So now we want to figure out what are A1, A2, and A3, so we can put this into here and integrate it. Now let's see. Let's do the same thing we did last time. Let's multiply through by this denominator, x squared times x minus 1. And say equivalent, we get on the left just the numerator, right? And on the right, I multiply x squared times x minus 1 times this one. One of the x's cancels, and I get a1 times x minus 1. I multiply x squared times x minus 1 times this one, and the x squared cancels, and I get a2 times x minus 1. So what I'm doing here is I'm just multiplying the whole thing through by x squared times x minus 1. You got this, right? I get just x plus 1 on the left, I get this, I get this. And then this one, when I multiply by x squared, x minus 1, I just get x squared. So a3 x squared. There it is. Partial fraction says I can have this form, so I multiply through by the denominator, I see this. Once again, I multiply out in group-like terms. Let's write this as x plus 1 equals, multiplying out, a1x squared minus a1x. Multiply this out, plus a2x minus a2, right? And then multiply this out, a3 x squared. Now I group the like terms, so I'll subtract the x plus 1 over here to get 0 on the left. This is important, right? To get 0 on one side, or this won't apply. I've got numbers multiplying x squared. I've got numbers multiplying x. And I've got numbers, not just constants. So let's see, it's a1x squared plus a3x squared. So this is a1 plus a3, all times x squared. Then I've got minus a1x minus, let's see, plus a2x. So minus a1 plus a2 And I forgot to subtract my x plus one, and I have to subtract the x plus one over here, so I've got minus x, minus one x, and then, from subtracting this x over. Maybe I should put it on the last step. So I'll multiply that, and let's subtract x and one from each side of this step, call it 0 equals this. Not any room to put it, is there? Minus x minus one. There we go. So I subtracted these over in the last step. And so now I've got minus a1x plus a2x minus x. Looks like that. All right. And then the constant terms, let's see, minus a2 minus 1. Once again, how many solutions does this have? I have a number times x squared plus a number times x plus a number equals 0. It's a quadratic equation. How many solutions does that have? We know the quadratic formula solves it every time, right? You get either 0, 1, or 2 solutions. So this equation by the quadratic formula will have either 0, 1, or 2 solutions if these are all, if these are general numbers. That can't be. This has to be satisfied for all x, right? Except 0 and 1. How can I satisfy this for almost all x? Well, only if all the coefficients are 0. If I make one of these 0, then it's a linear equation and only has one solution. If I make two of these 0 and this is non-zero, then it has no solution. The only way to make this have solutions for all x is to make all the coefficients 0. So that's this statement right here is completely equivalent to demanding that all the coefficients are 0. This one must be 0, this one must be 0, and this one must be 0. I'll write those down as 3 equations and 3 unknowns. A1 plus A3, and I'll leave a little space here, equals 0. And minus A1 plus A2 equals 1 to make this one 0. Minus A1 plus A2 equals 1 makes that one 0. And this one just says minus A2 equals 1 if I had one to each side. Minus A2. Or let's write it the other way. Let's write it as A2 equals minus 1. A2 equals minus 1 is the third equation. So I get 3 equations in 3 unknowns. And if I haven't made any mistakes, this system of 3 equations and 3 unknowns will have a unique solution. All right? That makes sense so far, I hope. Ask a question if you have one. Now I can use substitution. Or I can use elimination. However, in this one, it's kind of easier. I picked an example that's not too hard for a beginner here. Next time we'll do the more complicated examples. Hang on. They're just longer. They're not really harder. They're more involved is all. This one, we're lucky. We already have A2 is minus 1. So actually, we can start our back substitution right away. If we know A2 is minus 1, we can just put it into 2. All right, put these two together. And say minus A1 plus A2 is minus 1 equals 1. So we put this into equation 2, and it gives me this, which says what? Minus A1 equals 2. A1 must be negative 2. So now I've got that one. Now I've got A1 and A2. I can substitute those back into the first equation, right? A1 is negative 2, put into equation 1. So but you can see that if I had more complicated equations, I can still add a multiple of one equation to another. We'll do this some more next time to eliminate variables and then substitute in. So next time we'll do more elimination. I'll put this into 1 that A1 equals negative 2 and get negative 2 plus A3 equals 0. By the way, the reason I put these spaces in here is I want all the A1s over each other, all the A2s over each other, all the A3s over each other, so that if I have to add a multiple of one equation to another, it don't make mistakes. I'm more likely to get it right. So do this when you're doing the homework, and we'll exemplify that next time. All right, so add 2 to each side, and we find out that A3 is equal to 2. There it is. I have all 3 coefficients. I can say, therefore, by partial fractions, our original integrand, x plus 1 over x squared times x minus 1 can be written completely equivalently as a1 over x. We have, and a1 is, where was it? Minus 2, so it's minus 2 over x, right? Plus a2 over x squared, I just erased it, but a2 is minus 1, plus a3, which is 2, over x minus 1. There it is. This expression is equal to this one. We just undid the common denominator. So, when we want to integrate x plus 1 over x squared times x minus 1, we can instead integrate this sum, which its integral is minus 2 integral 1 over x, integrating this one. Right? We integrate the whole thing, and then the integral of the sum is, well, let's write it out. Integral minus 2 over x minus 1 over x squared plus 2 over x minus 1. And this one falls to all our previous techniques. All right? So we say integral of sum is the sum of the integrals, pull the constant out, it gives us minus twice the integral 1 over x, minus once the integral over x squared, plus twice the integral 1 over x minus 1. Each of those is easy, right? What is the integral 1 over x? That's just natural logarithm. And I get minus 2 natural logarithm, that's the value of x. What's the integral of 1 over x squared? Well, if we write 1 over x squared as x to the minus 2, we say integral x to the minus 2 is x to the minus 1 over minus 1, or minus 1 over x. X to the minus 1 over minus 1 is minus 1 over x. And then plus twice, what's the natural log of x minus 1? Again, I'm making u substitution, but u equal x minus 1. So du is its derivative dx is 1 dx. And so I just substitute out du for dx and 1 over u here. I've got twice the integral 1 over u to u when I use substitution. So this is minus twice natural log absolute value of x plus 1 over x plus twice the natural log absolute value of u. And now when I drop the last integral sign, I have plus c. And then the same thing as last problem applies. You can put these 2's up in the exponent, right? I can write this as natural log of I prefer to put these in the other order. We can let's rewrite this as twice ln u is x minus 1 minus twice ln x plus 1 over x plus c. Let's write it in this order. And then we'll say we can put the 2's up in the exponent. This becomes twice. This becomes natural log of x minus 1 squared. And we drop the absolute value because it's squared anyway. We won't have a negative number here. And then the 2 up here gives us ln of x squared, and I drop the absolute value because it's an even power. And there's my answer. And then I can combine logarithms. Ln p minus ln q is ln of p over q. This is natural log of x minus 1 over x squared plus 1 over x plus c. Now you can see that's quite complicated. I recommend on your homework, what you do is you do this by hand, because if you can't, you won't pass the test, right? This is what's going to be on the test, something like this. And then go back and look on your favorite integral calculator and see if you get the same answer, right? And it might be this form, or it might be this form or something, but you can see, and then write in your answer blank so you won't lose partial credit for putting it wrong the first time, because these are very complicated. All right, that one look okay? I hope. Well, I don't have time for a whole problem, but I can do one more illustration here. We made the note before, if the numerator has higher degree, what do you do to integrate it? what you should do is use polynomial division, which you saw in algebra. I hope you remember it. Maybe you remember synthetic division too. It's a special case of polynomial division that works for when you're dividing by x minus a number. Use polynomial division to rewrite it. When you rewrite the quotient after polynomial division, you'll get a quotient where the numerator is lower degree, and then you can apply this technique. So that's what we're going to do in that case. All right, so here's an example. Suppose I wanted to integrate this thing, x squared over x minus 4. Well, the degree of the numerator is big or greater. I said higher or the same degree. If it's the same degree, you also have to do this. The degree of the numerator is at least as big as the denominator. I can't go to partial fractions, but what can I do here? What you do is you do the division of x squared by x minus 4. And you ask yourself, remember how this goes? How many times does x go into x squared? It goes in x times. So I multiply x times x minus 4 and get x squared minus 4x. And I subtract down. X squareds cancel. 0 minus a negative 4x gives us plus 4x. How many times does x minus 4 go into 4x? So it goes 4 times. So I have then 4 times x is 4x, plus 4 times minus 4 is minus 16. And I wind up, this one minus this one is plus 16. Polynomial division says that the original quotient, x squared over x minus 4, is the quotient plus the remainder over the denominator. So it's x plus 4, the quotient that you get, plus the remainder, 16, over the divisor, x minus 4. So you rewrite it like that, and then instead of having to integrate this is easy to integrate. Right now, this is lower degree. In fact, there's no partial fractions even required. It's already reduced. You can integrate this. Lower degree on top always happens after you do the polynomial division. I would do a better one, but we're short on time. I just wanted to show you this is polynomial division.